And it's a pleasure to introduce Professor Jordi Corominas. I think many of you know him. He was the 2016 Varnes Medal recipient. He's an engineering geologist. He's now in the Department of Civil and Environmental Engineering. They've changed the name, I understand, at the Technical University of Catalonia in Barcelona, Spain. And the title of his presentation is Rockfall, Occurrence, and Fragmentation. And Jordi, I'll give you a 5-minute warning as well, okay?
Good morning to everyone. It's an honor for me to stay here and to give an insight of the work that we have done in the last few years in our research team. I have to acknowledge the work of my colleagues, Olga Mabruli and Roger Ruiz Carulla. What I want to tell you is about fragmented rockfalls, although I'm going to say a few words about rockfalls, fragmented rockfalls, and rock avalanches that maybe you are familiar with, but just in case to see what I'm interested in. A few words as well about new tools. We have just seen a good review of the monitoring tools available so far, so that I'm not going to go very far on this. And then I would like to stress about the point that when we talk about risk analysis, what is the maximum credible event we must consider? This is always a challenge for us. And also about rockfall fragmentation. This is something, a mechanism that we know that exists, but we don't know how to deal with. Okay, rockfalls, you know what are rockfalls? It's a detachment of a rock from a steep slope. And the particularity is the trajectory in which falling, bouncing, and rolling is the main propagation mechanism. And of course, there is no interaction between the moving fragments. A different concept is fragmented rockfall. It's very close to rockfall, but in fact, I would say it's very close to each other. But this term was defined by Evers and Hunger, in which they try to put the attention in the fact that there are many fragments going down, and there is little interaction between fragments, and they follow different trajectories. If we increase the volume, then we may face what it has been defined as a rock mass fall or a Boulomar mass, in which, of course, there is a huge mass moving down, but it's still the interaction between particles is weak. And for instance, this produces the biggest blocks. They travel farther away, so they are not transported, but they move individually, but probably there is an interaction among particles, and they will increase the internal pressures, kind of fluidification. And then if we increase the height and the volume, probably we will reach the rock avalanches, in which there is a rapid disintegration of the mass. It propagates as a digranular flow, and has some specific features that I will put some few examples, like reverse grading or crashing, comminution of the rock mass. In fact, there is a transition between rockfalls and rock avalanches. In fact, the concept of rockfall or fragmented rockfall is not based on the size, but is based on the propagation mechanism. And this is what makes the difference among them. What is the boundary between these processes? Not clear, because it's a transition, and probably these processes of individual and independent movement of the blocks and interaction between blocks is something that occurs in some cases, so the different mechanisms may coexist for a while in some of the events. Okay. We are interested, in my talk, I'm interested in fragmented rockfalls. What happens is when we deal with risk associated to these events, we must consider as well the possibility of having a big event. That means we should consider whether we may have rock avalanches or not in the same location. This is something that when we deal with risk, we must consider as well. Well, I think Claudio Margottini has made a wonderful presentation of the new techniques we have. This is a picture when I was doing my PhD studies many years ago. using the tape, and you see it's an old-fashioned. Now we have new tools, terrestrial laser scanner. We have a point cloud. We may obtain discontinuities, deformation, digital surface models, and this gives us a completely different perspective of the rock mass. We can obtain, extract a lot of information that we couldn't ever imagine, but we could do. So this is really a revolution. We may use monetary vehicles. We may just take digital photograph, and from this we may proceed all this. We may treat all this information to attain the, as Claudio mentioned. Sorry, yep. I think I should. We may obtain the stereo plots. We may obtain as well the size of the different joints outcropping in the rock mass, and also, well, from here we may, for instance, obtain with digital photography, photogrammetric model of the rock slope. From here we may obtain volumes. We may characterize the joints. We may just use these joints to cross this volume and obtain a discontinuity pattern. And from here, we may obtain how the rock mass is divided in small pieces. So we may obtain what we call the in situ block size distribution. It's a possibility that we can do now more easily than before. Again, with these techniques, we realized that we can make a kind of failure prediction. These are deformations that we can measure from different campaigns. Here we start, when we increase the blue color means the more deformation, and then we see how places where start having a larger deformation, finally they fall. So here again, we start having deformation, increased deformation, more deformation, and finally this falls. That means it's a way that we can measure this displacement and also obtain these creep curves that most of us we know. So we may try to make prediction, forecasting of the time of failure. You know that it's difficult, but we have these tools already now. And also we may identify the missing volumes, the detached rock volumes, and of course from here we may define where the rockfalls have taken place, and also to measure the volume of the missing rock mass. So with this, we may go to a relationship like this, a magnitude-frequency relation. And this leads us to a point that is interesting, because I usually work with hazard and risk analysis. And something that is fundamental for us is knowing which is the probability of occurrence of events of different magnitude. And these frequency magnitude relations, now we can obtain with these new techniques like the terrestrial laser scanner and others. Okay, this brings me to a place we have been working quite a bit for the last decades. This is a tiny country in the Pyrenees, is in the border between Spain and France. This is the tiny country of Andorra. It's really a small country, but is densely populated. This is the capital, Andorra la Vella and Santa Coloma. And as you see, is there, the village is located at the foot of the slope, a steep slope, more than 1,000 meters high, in which, in this area, they suffer frequent rockfall events. And they have done some work. Well, we try to analyze what is the risk in this area. To do this, this is the risk equation, in which we need to know which are the sources of the rockfall. There are multiple sources for rockfalls. We need to know what is the probability of occurrence of a rockfall of a given size. Once we know this, we need to know what is the probability of reaching a given point with a specific kinetic energy, which is the intensity of the rockfall. And then we need to know whether in this point there is an exposed element or not. and what is the vulnerability of the element. With all these components, we may determine what is the risk in this region, and we must do this for all rockfall magnitudes. And this is our challenge, at least the challenge we face, and we are having difficulties just to solve some questions that I will just leave to you. In fact, I want to raise more questions than giving answers to you. In this community, they have done a lot of work. They have worked putting rockfall fences. These rockfall fences work pretty well sometimes. In this case, there was a 5,000 kilojoules fence that was overturned by a big rockfall. Now they have been replaced by 8,000 kilojoule barriers. And also they have undertaken a planning trying to define which are the dangerous areas that can be built and that cannot be built. Of course, there are some existing buildings in the wrong places that were considered that they are too dangerous, and these buildings are restricted in uses. You cannot do everything there, just simply as a workshop and nothing else. You can store material but not be in there, and these are the buildings that have been affected. They have done a lot of studies, and they try to manage the hazard and risk as much as they can. The question here is, what is the worst credible event? Because all these protection measures they build are protection measures that work for a given size. The key question is, what is the size that we need to take into account? And this is not an evident answer. This is a list of the rockfall events in this area, 50 years of rockfall inventories. And with this we obtain that probably you know this type of power relationships between the magnitude, the volume of the rockfall, and the frequency of the rockfalls. This relationship is very nice. It has an exponent. This is quite common. This is a negative exponent that we have seen in many other places, in many other locations with rockfalls. Well, the point is, well, what should we do? We have historical record. So the question is, if we want to evaluate the risk for the future events, what should we do? We have a historical record with rockfalls of a given magnitude up to some few thousands of cubic meters. Should we, sorry again, should we extrapolate this record? Many colleagues suggest this. Many people state that this type of relation, that if you have a power law, you can extrapolate it. Well, what happens if we extrapolate this relationship in this case? Well, these are the results. So we should expect in this area, every 100 years, 10,000 cubic meter rockfall event, twice every millennium, 2 rockfall or rock avalanche events of 100,000 cubic meter, and every, let's say, in 10,000 years or 5,000 years, 3 events of 1 million cubic meter. If this happens, and we try to perform this type of F-N curves that some of you are familiar, we come out with an acceptable risk. So, well, what should we do? We should stop building here. We should say all the people move from here. This message will mean leave the country. This is the lowest area in the country. This is the lowest place. The other part is really mountainous, so they have no place to go. So is this the message we should send them? Well, but we said, okay, should we believe in this extrapolation? Which are the evidence for this extrapolation? So this is an aerial photograph in 1948. And this is a geomorphological map prepared by colleagues of us, two and colleagues. And this is the flat plain. These are the scree deposits. There are some debris fan or alluvial fans. This valley was formerly glaciated. 20,000 years ago, this was plenteous ice. the glaciers retreated 20,000 years ago, and this flat plain was formed 10,000 years ago. So if we have a plain, a fluvial plain 10,000 years ago, and if we had this recurrence of events, we should expect that these rockfall events of 100,000 or 50,000 or 200,000 cubic meters should be distinguished in the floodplain, should be there. We should expect 3 or 4 events of 1 million cubic meters. We should have expected at least 10, 15 events of 100,000 cubic meters. This means that the whole valley will be plenty of these deposits. And what we see? Nothing. These deposits are not there. We see the screw deposit, we see the floodplain, but there are no large rockfall events or rock avalanches there. So, well, why we should expect that in the future we could have this size of rockfall events with this probability of occurrence? This is our question mark. So we were not convinced of that. We tried to look what happened at the source. So we look at the rockfall source to the rockfall scars. I would say, okay, if we identify rockfall scars, we should have an idea of the past occurrence of rockfall events in the world. That means that we need to check whether we are able to identify these rockfall scars. So we did. We knew in this case, in Andorra, in this particular case, rockfalls are produced by sliding over a surface, that is the rockfall start sliding over a joint that is dipping towards the valley. These are these blue plains. And we have as well tension cracks, that these plains behind these plains are tension cracks for the rockfalls, and they're bounded by lateral, by lateral planes. So these are the boundaries of this rockfall scar. There are 3 main joint sets that control the whole movement. So let's see what is the size of these rockfall scars we see in the rock wall. So we did with a terrestrial laser scanner, and I'm going to go a little bit fast in this because we published this 5 years ago. So we identify all the scars. We try to obtain the area, the basal area of these sliding planes. We try to obtain as well the height, not the spacing, the height of each scar. And then when we had the distribution of the measured areas and the distribution of the measured height, we made a combination with the Monte Carlo simulation. We made an analysis of which are the volumes that we can produce with this combination of areas and heights of the scars. And after obtaining 5,000 cases, the largest volume we obtain is 3,000 cubic meters, not 1 million cubic meters, not 100,000 cubic meters. So, okay, we tried again, just looking at the cliff and assuming that all these cliffs are steep enough to fulfill the Markland conditions, the kinematic analysis. Let's see what would be the size that we could mobilize in this rock wall. So we could look for all the rock faces fulfilling the criterion, the first criterion that the slope angle is steeper than the deep angle of the joint. And also, we measure these areas, and we make an estimation that what could be the volume that can be mobilized in these cases in which have kinematically possibility of movement of these rock masses. We did the same procedure, and what we obtained was a maximum volume of between 25,000 and 50,000 cubic meters, and a maximum estimated sliding plane of 1,300 square meters. These volumes are bigger than the scar volumes, but even they are bigger, they are much smaller than the frequency relation predicts. So, well, then the question is there any upper boundary for rockfalls in the area? So, because I see that I'm exhausting my time.
5 minutes.
5 minutes? Well, I suspect this. Okay, this is what we see in our scar surfaces. That this is power law, but then if we try to extrapolate the power law, we see that there is a deviation. This is measured. This is not assumed. This is measured. And this is something that happens when you see other rockfall inventories. If you extrapolate the power law, the biggest volumes, they do not follow the power law. So there is a kind of deviation or cutoff, and this is the point. Do we have any geological explanation for this? Yes, we do, because we have seen that the joints that bound the unstable volumes, two of these main joints are faults. Fault systems that they displace the sliding planes. So you don't have continuity in your sliding planes because are interrupted by these faults. So the pattern in Andorra is close to this case rather than to this case because the unstable surfaces are interrupted by these fault systems. Well, so even though we cannot discard possibility of rock bridges as has been mentioned before. So can we accept a cutoff value for large rock falls in Andorra? This is the question. And if the development of the valleys may be accepted, provided that a risk management will include monitoring of the rock wall, because we know that large rockfall events are preceded by premonitory displacements, why not? So this is our discussion now. I move rapidly to the rockfall fragmentation. Rockfall fragmentation has a lot of consequences in the meaning that because the rock mass is fragmented, you reduce the energy, the kinetic energy. You reduce the runout distance of the blocks, but also, on the other hand, you increase the probability of impact on disposed elements. So you have a double effect. So we try to analyze the effect of this fragmentation. We have made some real-scale tests with a drop test of blocks. What we have learned from this test is that we attain the fragments follow also a power law, but the exponents of the power law changes. There are exponents that are very close to -1 and exponents that are very low. And what does it mean? That we have large exponents when we have a lot of fragmentation, smaller exponents when we have few fragmentation. And also the percentage of the block that has been broken increases with the exponent. That means fragmentation is controlled by the energy of the impact, and the higher the impact of the energy, the higher the number of blocks you obtain. We check this in the rockfall events, in the inventory rockfall events, and we arrive to the same conclusion. We have also a power law for the fragments. What happened is that despite all these curves, they look the same, the exponents are not. We see that the exponents may range from 0.5 to 127. And it's also an effect. It depends on the energy of the rockfall, how much energy you have to break the rockfall mass. The higher the energy, the higher the number of fragments, then the higher the exponent. This is what we found. And based on this, we prepared a rockfall fragmentation model in which we may start with a single block. This block may break or may not break. If there is no breakage, there is no fragmentation, both volumes will coincide. We may start with a rock of a given volume, and then we may come out with a range of volumes, a distribution of volume. This is the breakage. And we may start with a rock mass with an in situ block size distribution that simply disaggregates, so both relationships will coincide, or we may have a breakage of some of these blocks, and then we will have a different rock block size distribution. Based on this, sorry, I'm doing something. We propose a fragmental rockfall model that is already published, in which is a fractal model, in which the number of fragments that are produced depends on the number of initiators, and also from a couple of parameters. This is the probability of breakage, what is the percentage of block that is broken, and also this is the relationship within the parent block and the resultant blocks. This B relation. We modified a model of perfect with some improvement. Instead of using one single initiator, we started with in situ block size distribution, and also we gave a possibility that some of the blocks, they do not break. With this, we just checked this rockfall model, fragmental model, in a case in the Pyrenees. in the Cadiz, in which we had a 10,000 cubic meter rockfall event. It produces a young debris cover and some tens of scattered blocks. So we obtain the rock block size distribution of this deposit, measuring by hand. We expect to do this automatically in the future, but at this time was measured by hand. And also we obtain the volume of the initial rockfall mass, in which this volume was dissected by different joint sets to attain the in situ block size distribution. So we applied, we know this is the in situ block size distribution, and this is the resultant rock block size distribution. So most of the larger block has been broken to, we have less big blocks than initially. So this, what we see is that the number of the small blocks increases significantly when you have fragmentation, and that means we started from 6,000 blocks and we come out with 60,000 fragments. So it's 1 order of magnitude bigger number of fragments. So with this, we calibrate our model, the fragmental model. This green line is the results of the model, and you may see how this Rockfall fragmented model is able to, starting with this in situ block size distribution, to reproduce the same rock block size distribution. Okay, this can be integrated also in a Rockfall trajectory model, and once we include fragmentation in the model, we realize that results are significantly different. Sorry. This is the results without fragmentation. Many large blocks, they go farther. And here, once we include the fragmentation, only few blocks are able to reach farther distance. And we have an increase of trajectories because we have many more fragments that has been broken. And then we have a lot of trajectories, but less run-out distance. Just to conclude, we say that obtaining these magnitude frequency relations is one of the most challenging activities in landslide risk analysis, hazard analysis. We argue that this extrapolation in the cases like in Andorra may not yield reliable results, and this blind extrapolation has to be done with care because we may conclude that we are very pessimistic on that. In fact, we know that the distribution of large rock slope failures in mountain ranges are not random because there are some geological constraints on the volume. And in this case, we have seen that in Andorra, the presence of these fault systems restrict the size of the potential movable volume. And of course, the fragmentation of the rock mass produces a change in the energies and diversion of the trajectories. So it changes the view we have about the rockfall analysis. And the rockfall inventories indicate that the number of fragments may increase significantly, even 1 order of magnitude. So we must take this into account in our analysis. And the fractal fragmentation model is able to reproduce the fragmentation pattern observed, but we need, in this case, to be calibrated with more real cases. Okay, we have some of the results in our web page of our current project, the rock models, that you will see all this information and papers related to this work. Thank you very much for your attention.
Yeah. Thank you, Jordi. So we have time for one quick question. Any questions? I have a question, Jordi. You said for validating the maximum volume size in the floodplain, we don't see anything. Of course, that's the late Holocene surface. So you probably have a couple 100 meters of sediment accretion in the valley bottom. So did you do any geophysics to see block size underneath?
There has been geophysics because they had some wells exploiting and they didn't find any rock avalanche deposit. But anyway, the present surface is about 5,000 years old. So during these last 5,000 years, there are no deposits on the floodplain. So that means, well, we have 5,000 years with nothing.
Okay, I was wondering if there'd be immediately during debuttressing of the ice or whatever, you'd probably get a lot of movement. So maybe at the base of the
probably it will, but not recently. That's the point. So that's in the last 5,000 years, we have seen any big rockfall events or rock avalanche. So the point is why we should expect this frequency for the future.
Yeah, great. Thank you. Mm-hmm. Okay, thank you.
Okay,
good.
So I have now the pleasure